Okay, so this is chapter 2, question 2.11. It says in here that a test car travels in some sort of straight line along the x-axis, and we're being shown the car's position x as a function of time. We need to find the instantaneous velocity at points A through G. Okay, so the key part in here is instantaneous velocity. The instantaneous velocity, like in general, velocity is calculated as the change in your position divided by the change in time. And if the change in time in here is fairly large, then what you're talking about is something that's called like average velocity. And if you use the language of calculus, where you introduce a limit to this, so let's say that you took this time, this delta t, and you made it smaller and smaller and smaller in terms of its how long the time was for your observation. So and you took the limit as delta t approaches 0 on this expression delta x over delta t. What you're doing when you take the limit as delta t approaches 0 is you're shrinking the time frame for your observations. And then the velocity that you get from there would be now called instantaneous velocity. So in here, this v is an instantaneous velocity. So that's the technical definition of an instantaneous velocity. And if you recognize this limit process here, at the end of the day, the instantaneous velocity would be like the slope at that given point in time. So we're supposed to find the velocity, the instantaneous velocity at points A through G. And basically what we need to do is find the slope of the position graph at every point. At point A here, A lies on this line. And if we can just find the slope of that line, which, by the way, B also lies on, we will get the instantaneous velocity at A and at B, because actually it looks like A and B lie on the same line, so the instantaneous velocity will be the same in both time points. So let's see how we could get the slope of this line. What I'm going to do is I'm going to focus on this point right here, which would have coordinates of time 0, position 20. And then I'm going to look at this point right here, which has coordinates of time 3, like 3 seconds, I guess. And then the position there is 40 meters. And if we wanted to calculate the slope on that line, it would be the change in the y values divided by the change in the x values. The change in the y values, let's call that 40 take away 20. And let's call the change in the x values 3 take away 0. So that works out to be 20 divided by 3, which if we were to, use our calculator here, 20 over 3 would produce 6.6 repeating. So we can round that to 6.67. The units for that would be in meters per second. So meters per second there. And basically 6.67 would be the instantaneous velocity at A and also at B, because both of them lie on the same line. A line has constant slope. So once we found that the slope of this entire line was 6.67, that basically means that that was the instantaneous velocity at A and also at B. Okay, so we're done with that part. C, if we're moving on to C, notice that C, the point C, lies on a flat line. The slope of a flat line is 0, so the velocity, the instantaneous velocity at exactly point C would be 0 meters per second. Point D, let me just make some space for myself. Point D lies on this line, so we need to find the slope of that line. To find the slope of that line, what we do is we'd want to take this point here. The coordinates would be time 5 seconds, position 40 meters. And then let's take a look, that point there. That would be at time 6 seconds, position 0 meters. And then we'll calculate the slope of that line, delta y over delta x. So we'll do 40 take away 0 over 5 take away 6, which gives me 40 over negative 1, which is, well, negative 40. So our instantaneous velocity at point D would be negative 40 meters per second. That's what we would have here. And technically, if you look at E also lies on the same line as D. Lines have constant slope, so if the instantaneous velocity at point D is negative 40, at E would share the same velocity, the same slope, so negative 40 meters per second. F looks like it's a continuation of that, so I would say F is also at negative 40 meters per second. And G here lies in this point where we don't have a lot of data. But if you have taken calculus before, you would kind of tell that this is like a local min where the slope of that local min is 0. So at G, the instantaneous velocity would be 0 meters per second. So that's pretty much it for all the points there.